So welcome everyone to our plenary session. It is a great pleasure and honor to chair and present Professor Hashem Pesaran. Thank you for agreeing to join us today. Professor Pesaran currently holds the John Elliott Distinguished Chair in Economics at the USC, and he's an emeritus professor of economics at the University of Cambridge and a professorial fellow of Trinity College at Cambridge. Hashem is one of the most innovative and influential econometricians with several papers published in leading scientific journals, along with highly influential books on both theoretical and applied topics. The economics profession has gained much better understanding of both the power and limitation on econometric analysis due to his contributions. His early work dealt with the problem of model selection, testing, focusing on situations in which the hypothesis under considerations are separate or non-nested. Then he worked on the rectification, estimation, and solution of rational expectations models and the problem of application. More recently, Hashem's work has focused on the econometric analysis of heterogeneous dynamic panels with unobserved common effects and spatial dependence, panel unit roots, forecasting and decision theory, factor modeling, and variable selection with big data. Hashem's work has had an impressive impact on policymakers throughout the world, especially on several policy-making institutions. His work on global vector autoregression modeling has been used extensively by both private firms and public organizations such as the IMF, the European Central Bank, and other leading financial institutions around the world. Hashem has also played a huge role in advancing the applied work in the profession by founding the Journal of Applied Econometrics, which has developed into one of the world's leading journals for applied economic work. It was the first journal in our profession that promoted and ensured the replicability of empirical work, which is really important. Finally, Hashem was a co-founder of the International Association of Applied Econometrics, which has become a very successful forum for applied researchers. And here at the University of Cyprus, we had the honor to host the last pre-COVID and in-person conference. In sum, Hashem has substantially pushed forward the frontier of knowledge in econometrics and economics. Thank you again for accepting our invitation. Without further ado, I will give the virtual floor to Hashem.
Well, thanks to Andros, and thanks you also for Karim Abadir, who contacted me, and a good colleague and friend, and all the rest of you who have put together such a wonderful conference. And I was saying how smoothly is running and how much I enjoyed the documentation on how this conference is organized. Thank you again to organizers for inviting me. And I'm really humbled by a very generous introduction by Andros. Without further ado, let me share with you the screen for my slides, which I hope that you can hopefully see now. This paper is just finished, and we're hoping to release it in a couple of weeks' time. And it is joined with two of my pleasure to have two of my PhD students from Cambridge, Andres Pig, who is now Rotterdam, and Alan Timmerman, which hopefully most of you know, who's in distinguished finance professor in UC San Diego. So as the title says, this is about forecasting in panels. And I have been thinking about this problem a number of years, and we've been looking at the literature and found that basically there is not as much work done in this area as I would have liked to see. What we're trying to do is basically look at some of these issues. So I'm going to start with the introduction, look at the model, and develop some theoretical insight, which could help later when we look at the Monte Carlo. And then obviously there is empirical. We have three major empirical applications, which I'm going to share with you, and then make some conclusion. So the first thing is, as I said, there has been a lot of work on panel. I mean, amazing amount of work. I mean, the most cited papers in econometrics are on panel data analysis. Basically, most of them focus on parameter estimation and inference. For example, they allow for heterogeneity in a fixed effect, like a true fixed effect or other setup. But most of this focuses on the estimating a parameter of some time varying or time invariant regressors. They don't really consider the forecasting as such, because it's much more difficult when you have a large number of individuals to forecast all of them, as everybody knows about this. So then the question is that what is the literature? So we do look at it, but one of the major papers actually was written by Buddy Baltaji, which most of you know. He's done a lot of good work in this area. And before, there has been some studies who have looked at the panel, and there are more studies coming along, which they use Bayesian method mainly for very short T panels. There is a paper by Schofider and one of my colleagues at USC, Roger Moon, who are looking at these issues. But here we're dealing with panels which are moderate T, but large N. So in this paper, we're going to look at all these existing approaches, the ones we can implement. Obviously, there are so many ways you can implement these panel forecasting approaches. And then I'm pleased also to say we managed to get a simple test for basically forecast poolability rather than parameter homogeneity, which is different. So as I said, the major focus is on predicting the accuracy of individual forecasts, but for different N and T dimensions. And then we want to know how these N and T dimensions of the forecast of the panel interact with the degree of parameter heterogeneity. As I said, we propose basically a forecast poolability test, and also we look at combination forecast, which people have looked at. And then we do some Monte Carlo and look the Monte Carlo design specifically to look at the trade-off between the estimation uncertainty, which I'm going to articulate what we mean by that, and parameter heterogeneity. And then we have 3 applications, and these applications are house price inflation across the MSAs in the US, metropolitan statistical areas. There's about 370 of them. And then we look at the CPI inflation across different sub-indices, again in the US. And then we look at the returns across different stocks, thousands of stocks, and there are many different sub-periods. And the reason we chose these 3 applications, which is really all due to my co-authors, not myself as such, is basically because they have different degree of fit, which we call pooled R squared. So basically, we will see that inflation is most predictable, then is house prices, then return, which is least predictable, as we all know. So the baseline model is linear, but it could be quite complicated because when you write X could have lagged values, could have a special effect. It could have a lot of other variables that are predetermined. So X is the covariance that you want to use to forecast the Y, and there are N individual, and these are T time periods. Now, our focus is not on average of Y, so it's not an aggregate forecast. We're really interested on individual forecast of the units. And then the question is that obviously I can estimate this model assuming the betas are all different from each other. I can assume that the betas are the same and then forecast, or I can assume subset of betas are the same. And there's so many possibilities that I could entertain when I want to forecast individual units. So obviously it depends also on the T and N, especially T. So we start with a very basic assumption, then I show you we relax it. The typical assumptions are the errors are so uncorrelated. Obviously, that's not a really demanding assumption. If you go back here, as I said, if you think errors are serially correlated, oh, just add more lags of y or other variables so that ensure that the errors are serially uncorrelated. Otherwise, there's no point forecasting. Otherwise, you have to allow for serial correlation of the error in the forecast. So that's not the big assumption in my view. But obviously, you need to assume that the errors are heteroscedastic across I. They could be even over time, but we look at this short t, so the time variation in the parameters are already taken care of because we're dealing with relatively short t. Otherwise, if t was, we took a whole of the sample period and just want to forecast a few data points, that would be, the time variation become a real problem. So we are not doing that. So we're taking short t to deal with time variation. Okay, and then obviously assumption about the estimation parameters. As most of you know, forecasting, you don't really need to get unbiased estimators necessarily if the forecast is on a loss function. So most of these assumptions are made in order to get some theoretical results. So X's seem to be exogenous, but later on we'll see that we can relax it and we ask ourselves what happened if X was weakly exogenous. So that's not a problem. And then there is this assumption about the covariance matrices, like a correlation matrix for each unit, which is basically sample covariance matrix of the data, the predictors for unit I, which is QIT. And then we have the pooled one. So what is the, I haven't written what X is. X is like stacking all of the X's. So this X prime X is like sum of X prime I, XI. So like pooling the sample covariances, and that's capital Q. And then you scale it by T and N. So as usually the assumption are these are bounded and they have moments and effectively, usually people say, how do you know they have moments? Obviously, if T is very small, the universe of these may not have moments, the moments will not exist. And that's one of the major problems. So you have to have T larger than certain numbers, we call T naught, so that the moments of the inverse of this Q and Q pooled exist. For Q pooled is less restrictive, but one of the major problems in using individual unit is because the moments of the inverse of the Q often does not exist if T is small. And that has, in my, this is one of the major problems in analysis of short T panels. So these are technical assumptions. So what about the heterogeneity? Obviously, the beta, which is the mean of the beta, doesn't have to be the mean. Basically, is the average of the beta I when n become large. So it's just a definition which will be used. And then we are assuming the mean of eta is 0 and the variance is omega, which is omega eta. And then the degree of heterogeneity is defined by the norm of this omega matrix. Again, omega need not be positive definite because suppose it's singular, it means some of the coefficients are homogeneous. So that omega is not important. And also I'm going to talk about how this heterogeneity correlated with the X's and how they are correlated over I. That's something we come back to later. So that's the first thing is that the standard panel assumed that this heterogeneity is independent of X. And that's in my view, a suspicious assumption. I mean, people have looked at it. Heckman, when he was looking at return to education, realized that you know, an unobserved characteristic could be correlated with how many years of schooling you're going to have. So therefore, that's a possibility of correlation. So we're going to look at that. And then the other assumption is about whether the heterogeneity is correlated over individuals or not. It's a less worrisome. In practice, few applications have just that. There's a serious correlation, but you may want to take into account. So that's another issue that we need to address. So, okay, so let's look at two alternative forecasts. We're going to look at other methods. One would be just to use individual betas to forecast the unit, which seems to be what people do when they look at one country at a time, right? When people look at forecasting different countries at a time, they don't even look at other countries. They just look at US or they look at you know, France or United Kingdom, and that's what they do. Of course, the reason they do it because they believe T is large enough so that they can estimate this reasonably accurately. But in practice, in a lot of panel, T is not that large. So therefore, that's one of the issues that it may not be a good idea then to do that. So that's a forecast based on individual estimates. The second would be just to forecast individual units, but use the pooled estimate, which is, this is the pooled estimate. Of course, there are intermediate cases we're going to talk about. You can combine the two, you can do Bayesian methods and so on, but that's to highlight this is the big polar difference. So either you use the individual estimate or you use the pooled estimate. So basically, we always look at individual forecast, but we use different way of estimating the beta. You may say, well, if the individual engine is very large, using pooling for individual may not be a good idea. You're right, but there's a trade-off. So let's just look at that. So if you look at the mean square forecast error and then make the assumptions, which is you don't need to make assumption about the betas because heterogeneity doesn't affect individual units. So therefore, you don't need assumption 5 and 6, which relate to the heterogeneity of beta. So that's a good thing about individual forecast. You just look at one individual. You don't care about that individual differ from another individual or correlate with another individual. So that you're dealing with that. So that it gives you the usual result. And then, as I said, the problem is that conditional on this may exist, but what you need in forecast, you mean that unconditionally this should exist, which basically means that if t is short, this may not exist. So although it's order 1 over t, so when t is very large, everything is okay. But when t is finite, this could be quite sizable. This term here could be quite important. Not only because 1 over t is not too small, but also because this term could be large because Q inverse may not exist. The expectational. Now, let's now look at the pooled one. The pooled one doesn't have the 1 over t term here, but it has got 1 over n. So therefore, if n large, the uncertainty about pooling disappears. So that's good for n large. But then the problem is heterogeneity term enters here, which is omega eta. So the larger the omega eta is, the more serious it could be error at the level of if you use the pooled estimates to forecast individual units. But notice here, it's not just heterogeneity, it's pre-multiplied by x. It depends on what sort of x's they are. And therefore, it's quite complicated to look at the difference between this 1 and 2. So we're going to look at t small. That's why we made all those very strong assumptions to get some analytical result, but n large. Otherwise, if I say t is large, obviously 1 dominates 2. It's not even a brainer. That's the end of it. So the only way you can say use the pooled estimate is t is not large enough. So that's why the title of the paper says is estimation uncertainty, which is here, as compared to the heterogeneity, which is here. So then the natural thing to compare, obviously sigma I squared is common. You don't have to worry about that. So therefore, we compare that. These remarks I've already covered them. It's just pointing it out that the assumption we're making, some of them are needed for pooled, but not for the individual and so on. And also when you do individual forecast, you can allow for correlation of the x's and the heterogeneity, which is important. That I think this remark 5, I'm going to go over it. I think there's a little bit of mathematics, but I think it's quite revealing. So this is basically the pooled estimate. Okay, so you can write the pooled estimate like that. And then when you look at the error of the pooled estimate, it depends on 2 components, which is this with heterogeneity, because eta I is heterogeneity. And this is the usual error. But this one, under the very strong assumption we have made, this goes to 0. So what matters is this part. But this part depends on whether eta I is correlated with x prime I xi, not just with xi. It has to be correlated with this x prime I xi. So therefore, if you have this is non-zero, then the problem is even if all the assumption, classical assumption of panel holds, the pooling still would be biased, but the bias becomes to do with the correlated heterogeneity. So therefore, is correlated heterogeneity could affect pooled estimates. But what's interesting is that correlated heterogeneity does not affect individuals because each individual look at each I, and therefore eta I is not relevant. So because eta I is already in beta I, so therefore that's a big difference. That you also, in the Monte Carlo, we also try to consider cases where heterogeneity is correlated with X's as compared to case where they are not. So we find, not surprisingly, correlated heterogeneity is also an important consideration when you decide whether you want to use pooled estimate or not. Okay, so that's a result which doesn't seem to be really appreciated in the literature. So now we can now also consider combined forecast now. So we can now build up more methods. So another way would be to combine the forecast. You take the one based on individual estimate, based on the pooled estimate, just combine it by some omega I, the weights. Then you can obviously, you can work that out. It's straightforward. The problem is estimating these variances and covariances, as we all know. So, but it turns out that you can approximate them. And again, if n become large, the only thing would be, if you see that this is the difference between, if you look at this, this is the error of the heterogeneity, and denominator is the sum of the error of heterogeneity and the error of the individual estimate. Is like looking at the relative importance of heterogeneity to the total. Okay, the denominator is the basically estimation uncertainty and heterogeneity together combined. It's quite neat. It becomes like a sort of like a ratio of the two, and that leads us to the point that actually you can estimate it, although this estimate could be problematic because usually U of t is not large. This estimate could be difficult to use in practice because of the error they have. But anyway, we also, this is just a very simple graph since we don't have time. It just is obvious from what we just said. You can also simulate it and show that actually this is a degree of heterogeneity on the horizontal axis, and that's a risk about the parameter uncertainty and heterogeneity together. And you find that in effect that this individual one, because individual doesn't vary with heterogeneity, so the individual root mean square error is just this number, this line here, and then that's the pooled one, and that's the combination one we looked at. So combination one help, but the pooled one obviously is doing well when there is very little heterogeneity because you're pooling, and you get more precision. But as heterogeneity rises, there is a threshold that the pool start doing badly, which is not surprising. Now, so this is tell us that actually one way would be to look at the difference between the loss function from either using individual or using the pooled. Again, when n become large, this goes away. So that actually could also tell us that you can await testing poolability. So whether this is zero, like it's a threshold. And then this, we can then come out with this test, which basically says that if the null is an odd null, if you think about it, because it is looking at across I, so there was a familiar panel because n is going to infinity. So there's a lot of that you're testing, but I've learned how you can do these things. You can basically use like a standardized statistics, and that n going to infinity is not a problem, and you can get a normal test statistic out of it under certain condition, obviously. And then that's quite intuitive. What this statistics is basically looks at the estimate of the estimation uncertainty relative to the sort of the excess. So that is different from testing beta I being equal to all the same. So obviously if beta I was the same as the mean, this would be zero, right? So basically that's the whole point. The whole point of it is that in forecasting, you are not only interested on the homogeneity, but you're interested the product of the predictors and the estimators, whether that is interact with each other in a way that could affect the results. So now this is, so therefore what we could do, so let me explain what this test would do. So one way would be to combine, right? That's what we discussed. You can combine using these weights or some other weight, which is better, based on a better estimate, but that's weighting. Then the second is the approach is to say you pre-test, you use this test to see whether you should be pooling or not. If it says, if the test is rejected, you use the individual estimate. If the test is not rejected, then you use the pooled estimate. So that's switch. It's a pre-test problem. Then Bayesian method. There are a number of work done by Madala very early on, many years ago, and before that, Lee and Griffiths. So what they realized, the problem of, they were not interested in forecasting, but they were more interested in also estimation. But other people have used this. It seems a very good idea, but usually is when you do Bayesian method, you do some sort of shrinking, and the question is how you shrink. In this example, this is the variance of the, those of you familiar with mean group estimation, apart from R, when R is 0, is like using the allowing for heterogeneity to be estimated from individual estimates, okay? So basically, as R changes, you can then shrink more or less towards the individual estimates, depending on how we don't know these values, unfortunately, in practice. But it turns out that people have used these values, like the prior likelihood, they use these values, Bayesian, they use these values, and they use that diagonal with very small positive entries. I'm a bit worried about this. My co-authors have chosen these values when we come to the Monte Carlo and empirical, but there is always an uncertainty about how do you choose this. There's an option to do hyperparameter and then do another layer of priors on these parameters, but then aggregate, then do on some forecasting, but we are not doing it. But I think it could be a possibility. But I think it's a good idea to use Bayesian methods because of the trade-offs involved in the estimation and heterogeneity. So these are the methods. We also add a few other methods, median for basically estimates rather than mean estimates to choose. In other words, you can also use instead of use individual estimates, you could use median of individual estimates. That was my idea, because I thought I knew that when you don't have moments, individual estimate very unreliable. So the mean of the individual estimate may not be reliable, that the median could be reliable. And it turns out that, seemed to work well. I'll share the results with you in a minute. So let's just now look at some of the Monte Carlo results very quickly, and then just briefly go to the empirical. So the Monte Carlo is quite much more complicated than the setup, the classical setup used. So firstly, it is a lag-dependent variable here. So you use the lag value to predict. There's excess. Excess could be correlated with the rho. Rho is what we're going to, the heterogeneity, or a gamma, gamma and X could be correlated. So basically, you can have a lot of variation, both across individual and between the parameter and excess. And then we also allow for a lot of non-Gaussianity. It doesn't seem to matter so much, the Gaussianity here, because n is large. It just, my experience is that when n is above 30, Gaussianity doesn't matter so much. And my own experience in many panel studies, using very extreme, like chi-squared, or t-distribution is symmetric. It doesn't make much difference. But the chi-squared could be different. Even there, doesn't seem to be important. So we're going to look at different n. We look at the large n 500, but we look at t 20, 50, and 100. So 20 is supposed to be the small for this problem. If t is less than 20, like say 10, you shouldn't use any of this method. You should really, I don't know what you could do. Most of the time people use priors, and therefore your forecast depends on the priors, really, most of the time. And we use large number of replication to get rid of any replication uncertainty. So that's the model. So the aim again is to forecast y. And then what we do with heterogeneity, we basically allow for the x themselves to be heterogeneous in terms of their serial correlation. Remember, rho xi is the serial correlation in the x. And the mu x is correlated with the gamma. And then, so that's what the relation is. So gamma and mu x are correlated. And then we also, in order to allow for different degree of persistence, we choose rho bar. as rho bar become larger, there is more persistence, more dynamics. And it turns out that all of them, in a very complicated way, contribute to pool R squared, the pooled R squared. And in my view, pooled R squared has to be controlled in this Monte Carlo. I see a lot of people do Monte Carlo. They don't really look at what is the fit of the model. The fit of a model is the key in looking at Monte Carlo result. So in the supplement of the paper, you will see when it's released that there are pages and pages of algebra to make sure that the pooled R squared is controlled by the values of a low value and a high value as we go to common. So this is the Monte Carlo. So what we do, what are the estimator views? The individual one, the pooled one. We also use random effect estimate of Goldberger, who proposed it many years ago. Then median group, which I suggest, which is a new one. So therefore, what you do, you just take the median of individual estimates rather than the mean or the pooled estimate. It's like a pooling, but the median pooling. Then the forecast combination, then we deal with two methods, bias adjusted and unbiased adjusted, which I don't have time to talk about. Then this pre-testing type forecast, which we based on the poolability. And then we use the three methods of Bayesian, prior Bayesian. And if you look at all of them, there are 9 different methods. So for the measure of the accuracy, we use the basically look at the median of the forecast errors relative to the benchmark, and the benchmark is based on the individual estimate. So if this number is above 1, it means that they're beating the individual estimate. So pooling is a good idea, or some other method. If it's below, if it's below 1, it's like beating. Sorry, I made a mistake. If it's below 1, it means that the method under consideration, the J method, is beating the benchmark and vice versa. So let's just look at the results. It's difficult for everybody to see. Firstly, this is when R squared is very low. Obviously, N is all 500 to all of them, and these are all the 9 methods. I'm going to summarize very quickly, but I just wanted to show you what this means. These are means to do with basically the degree of heterogeneity. And this is to do with the correlation of the heterogeneity. So this zeros means that the heterogeneity is uncorrelated with the x's. This 0.5, it means they are correlated. Okay, but then these are the degree of heterogeneity. So therefore, this way the degree of heterogeneity rises without correlation, uncorrelated heterogeneity. This is another way. So when you have 0, 0, it means a vanilla case where you would expect pooling doing best. And you do best, right? You do very well. When t is small, you do very well. But as t becomes larger, your gain is declining relative to the individual estimate, obviously, because eventually individual estimate would win if t becomes larger and larger, or become equal to the pool. So therefore, if you believe there is no heterogeneity, pooling is a great idea. And now, whether you use random coefficient, or whether you use mean group, or whether you use all these other ways, it seems that you just pool. But in practice, we don't know the heterogeneity. So that's why maybe these likelihood methods, or PF, which is the poolability forecast test, which combination, or some combination forecast, could do better, or the median, which is another way. So that is why it's important to consider all this method that we looked at, to look at the trade-off. The other thing, if you look at this, is R squared 0.2. Let's just show you what happens if R squared goes from 0.2 to 0.6. It's the same table, but let's go back again. Here is when heterogeneity starts to rise, but t is small. Because t is small, individual estimate have very imprecise parameter values. So therefore, still pooling is beating the individual estimates, even when the heterogeneity is become large, and even when the heterogeneity is correlated, right? Still, a pool estimate, a standard pool estimate, doing well, because R squared is very low. But then let's look at R squared 0.5. That's not true anymore. So when you don't pool, it's fine. Doesn't matter whether R squared low or high, when there is no heterogeneity. But as soon as the heterogeneity starts to rise, you're doing very badly. And if you have correlated heterogeneity, you do a little bit worse than before, but not that much. I was surprised by it. That's because it's to do with also the t very small. So when you have dynamics, and everybody knows, those who are with dynamics, when you do individual estimate, remember you have lag value, there is a bias, 1 over T bias, which is quite large. But as T become larger, then definitely when you have heterogeneity, you shouldn't be pooling. But R squared is now 0.6. So therefore, the fit plays a very important role in the outcomes. So what is the summary of all of this? We also look at the quality of the forecast. In other words, how often a forecast beats all the other ones, how often the forecasts do worse than anybody else. These are really developed by Alan and Andre. They're very useful measures, and then these are all to do with that. So given the time, I just don't want to, we don't really have time to go into detail of how these things are done. Just
we have 5 more minutes.
Yes, that's what I think. So basically, effectively, what the bottom line here is, if you look at these results, that the pool forecastability, doesn't matter whether R squared 0.6 or not, it does as well or better than either of the methods. But Bayesian method does reasonably well, and combination method as well. But it depends on R squared. There is no really universal conclusion I could make for you, unfortunately. And in fact, this is also reflected in the 3 empirical applications we have done. So this is the house prices, which is quite complicated forecasting. We do allow for the spatial effect. We do allow for the regional and countrywide effects. But then they call it SAR model, SAR X model. SAR model does very well. The R squared, and also the window we use is 60 observations, it's quarterly, so it's not very large. As I said, we want to have short T, and then we try many forecast estimation. And then if you look at this forecast, you find that in this example, pooling does really well. The differences, I mean, again, if you look at how often they beat the benchmark, the median group does really well in these examples. But the differences are not that much. So basically means some form of pooling is a good idea on house price. I think because of the correlation across sector, across MSS, and over time, it's very persistent. So these are suggest that you have only very few observations. You can't estimate house prices for a particular region. So better to look at all of the regions together. It's probably not surprising. Again, given not have the time, and this is just a graph of what these different methods are doing. Now, if you look at inflation, now inflation is very persistent and the fit is very large, right? As I said, the higher the fit, you would expect the more the heterogeneous method works, and pooling would not work. And if you look at the result, it's exactly the case. So in this example, the pool method won't work. These are higher than 1. These values. But then if you look at the optimal combination method, or you look at the shrinkage type method, they do much better. Okay, so you need to mix it. So here, pooling is not a good idea. But if you go now to the stock returns, here we have a large number, 23,000 individual US firm stock returns, and over a very long period, the R squared is almost 1% at best, or maybe 0. So if you look at it, you get negative result if you use individual forecast. But what is interesting that a lot of people, like in finance, they said if you use just the mean, prevailing mean, that's better. It actually is not true. In our analysis, surprisingly, most of these methods beat just the mean forecast. So basically, these are the results. But again, you can't make any definite statement here. So the higher the fit, just one quick I can argue, when the fit is high, let me now conclude. When the fit is high, there also you can decompose these results. But then when the fit is high and there is heterogeneity and correlated, it's better to use combination methods, either Bayesian or the methods we suggest. But if the level of the fit is very small, like in the forecasting of stock returns, it's better to pool. So basically, it's not a good idea to look at individual one. If you increase the observation from 60 to 120, which we did, and then so it doesn't make much of a difference because there is variability now, which then model not stable. So the bottom line here is that forecast combination and shrinkage method offer insurance against poor performance, and forecast combination in particular seem to perform well across the board. Obviously, the shrinkage method depends on the shrinkage parameter. The good thing about the forecast combination is there is no parameter that the investigator should choose arbitrary. You just based on the estimates of the individual forecast. So it seems the conclusion is that if you knew the heterogeneity about your models, the degree of fit, you could probably direct your analysis to pooled or individual, but in general, it's better to look at combination methods. Of course, for T20, we talk about, if T is less than 20, I think it's an open game, how you deal with this. So I'm going to stop here and give sort of a floor to you guys to have any question or comments you may have. I appreciate your patience.
Thank you so much. Any questions? Ioannis Karavias.
Hello. Hello, Hashem. Thank you very much for your interesting presentation. I would like to ask if it's worth considering, or if you have considered the group fixed effects estimator as a middle way between the pooled estimator and the individual estimates. I've been thinking that as heterogeneity increases, perhaps you can gain something by assuming that there are some groups in your panel.
Yeah, you're right. I mean, the problem is you need to decide how to group them, right? So I think that this is often a difficulty, because using the data to decide the grouping, that's like a, like a pre-testing again, right? I think you can do that. So as I said at the beginning, it's open field. There are so many possibilities. It's mind-boggling, especially N is large, which often it is, like in the stock returns or in house prices or in looking at even across countries. It just suggests to me that even if you're interested in forecasting one unit, you better think about the whole broad spectrum of units which could be related to each other. But then you're right, then you could group them. If you can group them, then you can do better. So MSA is a kind of a group in a way already. Remember, MSA is already decided based on population density and other related issues of migration and so on. But nevertheless, they may not be optimal grouping. But you're right. You could also consider grouping techniques, which are like there are a lot of high dimensional techniques which they use like random forest or related techniques to group first. But there are a lot of parameters there people use in order to group, right? Then it affects the outcome, right? So therefore you need to sort of bear that in mind. Like the Bayesian techniques are very good, but you need to fine tune the parameters.
Thank you very much, Hashem.
No problem.
Thank you. I have one question. I was wondering whether you considered model averaging methods, in particular like jackknife based on cross-validation, given the presence of heterogeneity.
Remember, we're dealing here, we're dealing with an individual. So therefore, what you're suggesting, we need to develop many models for the same individuals, right? Mm-hmm. So yeah, that's what I just want to clarify, that's what you meant. So we do have, at the moment, we have a number of models, which we, like when we did both stock returns and when we did the house prices. For example, in the house prices, we had the SAR and then we had the SAR X model. So we do have, but we didn't try because there are not enough models. But you're right, it's possible that you can combine basically averaging across models for each individual as well. You could do that. But I don't think that would solve the heterogeneity problem, because if you look at each individual model, it's still subject to the sample uncertainty when T is small. Many of these techniques people use, they often assume T is large. In fact, I just talked to some of my students, they say, okay, I say, under what condition do you think least square is valid? They say, oh, when the rank condition is satisfied. But that's not true. I mean, the right condition means that you can compute the least square estimate, but you may not have no moments. That's the problem. So therefore, if you have no moments, it means that you cannot infer anything about the period you look at to the period you haven't looked at. Because to make inference, you need generalization. Generalization means that it should come from the same distribution, right? So therefore, I can guess. The trouble, therefore, is the same issue, that if I went to do model averaging and level of individual, then I have this issue of have imprecise estimate I'm adding together. I don't know what's going to happen, but it's worth trying. One possibility would be to ask yourself whether you could pool and model average. So I don't know how. I haven't even thought about that. That occurred to me now. That's one possibility. That basically you say models, but certain parameters are common across these models. Like, for example, the model is structural model, so something is elasticity, and we know the elasticity of something is very close to be similar across these models, right? So basically, I don't know. I mean, that's more demanding because you need more structural thinking about this to apply this technique. But it's a worthwhile thing to think about.
Thank you so much again. Thank you again for this wonderful talk.
Thanks so much. And if you have any comment, please send me an email and then I'll pass it on to my co-authors. It will help us to finalize the paper and release it, as I said.